Students, we are going to another very important topics from the photochemistry. This is called the laws of photochemistry. I can say that today's discussion is the foundation of photochemistry. If you could understand these topics very well, your journey in photochemistry will be so smooth. Therefore, please watch carefully, make the notes, and read more. Find any difficulties. Let us discuss in future and clear it. We will go to three laws. The first law is Groth's-Draper law. Groth's-Draper law. The first law in the photochemistry. This is the law. Suppose you have a sample. To this sample, a light is incident. This is called incident light. Light beam is incident. Photons are incident. Okay. Now here the sample and light meets. What will happen? Lot of process will happen. Some will be reflected. There will be reflection and there will be transmission and there will be some absorption and absorption, there will be emission and there will be refraction, etc. Okay. When light and matter meets, lot of phenomena will happen. Absorption of light will happen. Transmission of light, that is, some light will be transmitted. Refraction and reflection will happen. Bending of light, that is refraction. Reflection just return back. Emission also happens. All are different phenomena. Dear students, you should understand all these ideas carefully and distinctively. Okay. Now the law says that, okay, the photochemical change or the chemical change in photochemistry, the chemical change will be caused only by the absorbed radiation. Okay. In photochemistry, the chemical change will be caused only by the absorbed radiation. Fine. That is the Groth's-Draper law. Only absorbed radiation can cause the chemical change in photochemistry. Understand? Only absorbed radiation, absorbed photon can cause the chemical change in photochemistry. This is the first law. Now we will go to the second law. Students, we will move to the second law. The second law is called Stark-Einstein law. Okay. This is a law based on the quantum property of light. That is, light is emitted or absorbed, not continuous but discontinuous in the form of quantized particles. That is the dual behavior of light or quantum principle of light. What is the quantum principle of light? Light is emitted or absorbed, not continuous but discontinuous in the form of small energy packets that's called photons. Therefore, you have a sample, lot of sample, A samples, okay. You are sending light to the sample in the packets, HNU packets. The law says that each molecule or atom absorb each photon. One molecule absorb one photon only. That is, this goes to here, 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 this goes to here. Okay, each molecule absorb each photon. Okay, 1:1 relation. Molecule and photon has a 1:1 relation. If you have 1 mole of molecules to be absorbed, you should send 1 mole of photons. Okay, this is called a Stark-Einstein law. Okay, the energy of light absorbed by 1 mole of photon is called E or Einstein. It's called Einstein. What is 1E? 1E is equal to 6.022 into 10 raised to 23 into HNU. HNU is the energy of 1 photon. 1 Einstein is this value. The unit is joule mole raised to minus 1. Joule mole raised to minus 1. Okay. Therefore, this is called the Stark-Einstein law. Now, based on the Stark-Einstein law, we have a concept that's called quantum heat. We have a concept that is called quantum heat. Okay, quantum heat. Quantum yield, that is phi. Phi is equal to. That we have said that a single molecule absorbs single photon. Okay. Yes. Therefore, each molecule, suppose I am a molecule. This A is a molecule. It wants to do a photochemical reaction. Therefore, it should absorb a light. Okay. Therefore, number of molecules absorbed is equal to number of photons get absorbed. Therefore, quantum yield is equal to number of molecules absorbed divided by number of photons absorbed. Number of photons absorbed. Okay. Or quantum yield is equal to all molecule absorbed. Suppose all molecule which absorbed give the reaction products. Therefore, we can write number of moles of molecules absorbed. Here I made the moles. What is the 1 mole? Number of Einstein. Because 1 Einstein is 1 mole. number of Einstein or number of moles of Einstein. Number of Einstein, that's left because one Einstein for one mole. Now next is the quantum yield, another equation for another relation for quantum yield is number of moles of product formed, because all molecules absorbed will give the products, divided by number of Einstein. And according to Stark-Einstein law, the quantum yield must be 1. We are expecting that. Because each molecule absorbs each photon. Absorbed molecule gives products. Very simple. Quantum yield is equal to 1. But let us take some example. Reaction and quantum yield. Okay. 2Fe2 plus I2 gives Fe3 plus 2I minus, quantum yield 1. Simple. But if you take N2 plus H2 plus Cl2 gives 2HCl, this reaction quantum yield is 10,000 to 1 lakh. If you take this reaction, decomposition of ammonia, quantum yield is 0.7. Therefore, in many cases, you have quantum yield greater than 1 or less than 1. Here is the only case where quantum yield is equal to 1. Here is only 1:1 relation is followed. Here is not 1:1 relation. That is, look at it here. Greater than 1 means number of molecules absorbed greater than number of molecules, the number of Einstein, or number of moles of product formed is greater than number of moles of Einstein, or number of moles of product formed, or number of moles reacted divided by number of Einstein. Here number of moles reacted is very much greater than number of Einstein in this case. Here number of moles reacted is less than number of Einstein. In this case, number of moles reacted or number of moles product formed is equal to number of Einstein. Okay, therefore quantum yield is not always equal to 1. Therefore something more complicated is involved here. Okay. Now, why quantum yield is greater than 1? Why quantum yield greater than 1? Okay. Let us take an example. Let us take the reaction Hi plus H nu gives H2 plus I2. Here the first Hi molecule gives H nu. You are getting H radical plus I radical. This H radical again react with another Hi gives H2 plus I radical. Okay. Then I radical react with this I radical gives I2. Okay. Actually, look at this reaction. When you balance, 2Hi gives I2 plus H2. But in this case, quantum yield, number of molecule absorbed, only this molecule is absorbed. Sorry, number of molecules reacted, that is 2. Number of molecules reacted is 2 after balancing. Number of moles 2. But how many photon absorbed? 1. Therefore, quantum yield is 2. This is because only the photon, not only the photon, but also one of the reactant also initiated the reaction. Okay? Yes. Not only this photon absorbed and molecule break away, but one of the products, break products, this should be like this. It should be half H2. It should be half H2 by I2. But this is not the case. One of these products again reacted with another molecule. Yes. Therefore, the quantum yield is greater than 1. The quantum yield will be greater than 1 if there is chain reaction. If there is chain reaction. Or propagation step. Or propagation steps. Therefore, quantum yield will be greater than 1 if there is chain reaction or propagation step. Now, why quantum yield is less than 1? Quantum yield is less than 1. Less than 1. Because, suppose a case, you have a molecule AB plus H nu. It gives AB star. This AB star deactivated to AB plus H nu. Suppose you have 100 this, you got 100. 50 deactivated. And the other 50 gives A plus B. Okay, therefore 100 molecule, you have 100 photon. Okay, therefore in this reaction, only 50 is reacted. 50 is reacted. Only 50 is reacted. But how many absorbed? 100. Therefore 0.5. 100 absorbed, but quantum yield is number of moles reacted. Only 50% is reacted. Half mole is reacted. Okay. Therefore, quantum yield is less than 1 if there is any deactivation process happens. Okay. Now, application of quantum yield. Application of quantum yield. Let us discuss what are the applications of quantum yield. Let me check the video. Okay. Applications of quantum yield. First is, what is the quantum yield? One is number of moles reacted or produced divided by number of Einstein absorbed or number of moles of photons absorbed. Now, for first application, helpful to determine concentration of reactants or products, determination of amount of light absorbed. It also helpful the wavelength of light absorbed, the wavelength or frequency or wave number of light absorbed during the reaction. Okay. Now these are some applications of quantum yield. Now we can solve some numericals from this side. Okay. Very important. Students, let us do some numericals. Okay, let us radiation radiation of lambda 2500 angstrom was passed through, let me check the